to Math 31. This is a lesson on quadratic inequalities. Quadratic inequalities, and then the next section, which are rational inequalities, very important sections. The skills you work with here get used over and over again in this course. So you want to get mastery of it right now. And it's not difficult. It's just a sort of a labor-intensive sort of procedure. So let's start on a few questions. To determine the solution set of the following. So x squared minus x minus 6 is greater than 0. And you notice I've got a number line, or what appears to be a number line, and then a sort of a grid setup. That will be explained as we get to it. Thing is, inequalities that we've seen so far, the linear ones, and then also the absolute value ones, can be solved a certain way, following regular rules. But when you start getting into quadratic or higher degree expressions, it doesn't work quite so simply. And there's a specific method that is required for them. So when we see something like x squared minus x minus 6, we factor it first. So this would break down, if you factor it carefully, would be x plus 2 times x minus 3 greater than 0. Now the mistake that people make with it now is that they set each one of those factors to 0, and they go x is greater than negative 2, and x is greater than 3, and that's wrong. Because the thing you've got to be aware of with quadratics, or anything with more than one factor to it, is that you're constantly comparing the signs of the individual factors. For example, if x plus 2 is positive, and x minus 3 is positive, both factors positive, then the product will be positive. If they're both negative, though, then the product is also positive. And then if one is positive and one is negative, then the whole thing is negative. And it's hard to keep track of all of that. So the method, what I've got set up, will help us with it. So whether you do it by looking at it or whether you do it by solving, you need to find the zeros of each factor. Now most of you won't bother writing this out. You just take the x plus 2 and you set it to 0. So you get the 0 is x equal negative 2. It's the root. And the way it works for a 0, x equal 3 is the other one, that's where the sign changes for that particular factor. So on the number line, I indicate that negative 2 is one of the zeros. And then I write here, this is the very common way to express it, I put the one factor there, x plus 2. And then I put the other factor, x minus 3, so the full factor. And then I indicate on the number line what the 0 is, which is 3. And then down below the two factors, I write this as function f of x. So I will name this function f of x. And this whole procedure is referred to as interval analysis. And then I take each factor, like I take that x plus 2, and knowing that the sign changes at negative 2, I indicate where it's positive and where it's negative. So for example, if x was equal to, say, 0, let's say, and you plugged in 0 into that factor, 0 plus 2 is positive. In fact, that factor will be positive for all x values greater than negative 2. And so I just indicate that by putting a bunch of positives. And if you substituted an x value that was smaller than negative 2, say negative 3, negative 3 plus 2 is negative 1, it's going to be negative forever to the left of x equal negative 2. So now I know the behavior of that factor. Do the same thing for x minus 3. And because the 0 is 3, that's where the sign changes. The sign can only change at that point. And if you picked an x value, say 4, it will give you a positive sign for that factor, just like it'll be negative to the left. And then we just compare. So if x plus 2 is negative and x minus 3 is negative in these sections, it means the product is positive. A negative times a negative is a positive. So that tells me that the function itself is positive when x is less than negative 2. And then for the interval from -2 to 3, positive times a negative is a negative. So that tells me that the function is negative in that interval. And then finally, if x is greater than 3, a positive times a positive is also a positive. So it means that the function is positive when x is greater than 3. So we end up with this statement. The answer to the question is x is less than -2, or x is greater than 3. So in interval notation, which I haven't been doing for a while, -infinity to -2, open, in union with 3 to positive infinity. And you do not need to check these ones. It all comes out in the interval analysis. Let's do another one, or let's do more than another one. X squared plus 7x is less than or equal to -10. The thing of it is, these ones always have to be set to 0. Reason for that is 0 is the border between positive and negative, and that's what we care about. Not a big deal. We take everything over, or the 10 over. X squared plus 7x plus 10 is less than or equal to 0. And this one factors nicely. Breaks down into x plus 5, x plus 2 is less than or equal to 0. Now, I'm not going to take the time to set each one of them to 0 and solve, because you can usually identify the zeros simply by inspection if they're fairly simple. So x plus 5 is one factor, x plus 2 is the other factor, and I'll call the whole thing f at x. Now, that being said, x plus 5 will change signs at -5. So if you picked an x value that was bigger than -5, say -4, when -4 plus 5 is positive, and that'll always be the case. And then negative if you're to the other side. And x plus 2 has its 0 at -2. So I just draw the little dotted line down there. And its sign will be, positive to the right of -2 and negative to the left. So that just means pick any number like 0 that's bigger than -2, plug it into the factor, and see if the sign's positive or negative. It won't change anywhere else because it only changes at zeros. So f at x, if a negative factor times a negative factor multiplied, you get a positive. And then a positive times a negative would mean that interval is negative. Positive times positive is positive. So therefore, we want it to be where it's less than or equal to 0, which means where it's negative. So question is, where is f at x less than or equal to 0, i.e. negative? And the answer would be between -5 and -2. I'm going to go right to interval notation, so -5 to -2, and with a closed interval, because we in this case are including 0. So I'll say negative or equal to 0. That's the method. Let's try a few more. 2x squared plus 3x is less than or equal to 5. Only thing that makes this one more complicated is the quadratic itself. And once again, I'll remind you that it's a good idea to pause me, go through the question yourself, and then compare the answer afterwards. So we bring the 5 over. Now watch the factoring. I know that everybody here can factor well, or I hope they can. We actually do a factoring review in a short time. So the 2x squared breaks into 2x and x. This is the way I'm going to factor this. And then we have to break that 5 down into 5 and 1. The signs will be positive there, negative there. So you check that out. But you'll see that it will break down into 2x plus 5 multiplied by x minus 1. and then that's supposed to be less than or equal to 0. So 2x plus 5 is the one factor. X minus 1 is the second factor, and put them together, you've got f at x. And then the thing of this is, we identify the zeros. Now, if you're having a problem with 2x plus 5, you probably won't. But when you set it to 0, 2x is equal to negative 5. X is equal to negative 5 over 2. So it means that the 0 for that is negative 5 over 2, or negative 2.5. And then x minus 1, it's going to be it's going to have a 0 of 1. Now, if you picked values of x that were bigger than negative 5 over 2, say negative 1, or 0 would make the most sense, you'll see that that factor will become positive. So if x was 0, 2 times 0 is 0 plus 5. It'll be positive forever. Negative to the left of that. And then x minus 1, if you picked an x value bigger, it's positive. If you picked an x value smaller, it's negative. And then we can take these two factors together. A negative times a negative is a positive. Then a positive times a negative gives us a negative. And then a positive. So we're seeing the same pattern for all of these ones. And then when we want where it is negative, that is less than or equal to 0. So our interval inclusive is going to be negative 5 over 2 as a lower limit, positive 1 as the upper limit. X squared is less than 3. This one isn't anything too remarkable. Only thing to be aware of with this question is that it is a slightly different looking quadratic. You bring it over to one side. Make sure you factor it properly by taking out a common factor. So x times x minus 3 is less than 0. So our two zeros, the one factor is x, the other factor is x minus 3, and then f at x down below. X will have a 0 of 0. And then x minus 3 would have a 0 of 3. So this is no problem for the x. Wherever you have an x value that's positive, it means that factor will be positive. And if it's negative, it's negative. Nothing happening there. X minus 3, pick an x value bigger than 3, and it'll be positive, and then negative to the left. So f at x is positive there. Negative, positive. So you're seeing the same pattern. We want it to be negative. Now this is an open interval, so we're going to be from 0 to 3, open. Now these ones can be checked easier. I mean, but you don't have to check to see if there's something, built into the equation that makes it wrong, or the inequation. You'd be just checking, your algebra basically. But if you plugged a value between 0 and 3, say 1, into the inequality, you would get a true statement. And same thing if you were outside the interval, you'd get a false statement. So checks don't matter as much, but some people still like to do them. Now, I'm going to move through these next ones, and there won't be as much algebra in some of them. But x plus 2, x minus 3, x plus 4 greater than 0. Already you're noting that this is not a quadratic. And the reason I draw your attention to this is that because they work the same way. Even if you have 3 or more factors, you just indicate each factor and call the whole thing together f at x. Find the zeros for each one of them. And x plus 2 will have a 0 of negative 2. X minus 3 will have a 0 of 3. And then a little tight for space here. In fact, I'm going to change this negative 2 to negative 4. And then I'll put my negative 2 in the middle. That'll do it. And then go through it factor by factor. So the method is identical no matter how many factors you have. So x plus 2, pick a number bigger than negative 2. It's positive to the right. That factor will be positive. negative to the left. X minus 3, pick a value, and it'll be positive to the right, negative to the left. X plus 4, pick a value for x bigger than negative 4, and that factor will be positive to the right, negative to the left. And now the only thing is we've got three factors to consider. So for to the left of negative 4, this interval, negative 3, negative, negative, negative multiplied together is negative. And then between negative 4 and negative 2, a negative times a negative, two negatives will give you a positive. Remember, you just count up the negatives, and an odd number of negatives produces a negative product, and an even number is positive. Here you have one negative, so it's negative, and this is positive. And we want where it's greater than 0, so we want positive, so we want there and there. So it's an open interval between negative 4 and negative 2 in union with x being greater than 3. So that would be 3 to upwards forever. When you get to ones like quadratics, it gets more complicated. It's a lot harder to just tell what's going on by inspection. So this method is particularly useful for ones like that. The number 6 throws another curveball at us. It's still a quadratic, but the problem with this, 2 minus x, when you find the 0, and again, stop me at any time if you want to do it on your own, really recommend it, you get a 0 of 2. So that's not a problem. But there is one problem that will arise from that. So here's x is 2. And then the other 0 is negative 1/2. You can check that out if you'd like. 2x plus 1 set to 0 will be negative 1/2. The problem is this. Because of the reversal of this factor, 2 minus x, if you picked an x value bigger than 2, say 3, you'll see that that factor will now become negative. So up till now, it was always negative to the left, positive to the right. Here it changes. If you picked an x value like 0, something smaller than 2, then you get a positive. So you have to be aware. And then 2x plus 1 is conventional. It's positive to the right of negative 1/2. And then negative to the left. And then we take the two together. F at x will be negative, will be positive, and will be negative. And we want where it's greater than or equal to 0. So it's going to be the closed interval between negative 1/2, lower limit, and then 2, upper limit. So really, it's all about being aware for things like that, 2 minus x. Number 7, I'm not going to bother doing because it's nothing, no new ground being broken with that one. Number 8, however, has got some things on it that might be interesting. X squared plus 5 times x minus 3. Now this is actually a cubic as well. But the thing of it is, this, first off, won't factor. You cannot factor a sum of terms like that. And you could try. If you set it to, and you can't solve it either, x squared is equal to negative 5, there's no solution. So therefore, no 0. Now, if there's no 0, it means the sign does not change. And all I'm going to do is keep it in that form, x squared plus 5. And I'll have the other factor there, x minus 3. And the reason for that is that x squared plus 5, we've seen this sort of thing before. Whatever x value you select, square it plus 5, it is always positive. So we include that in our interval analysis. This is always positive. Just write it like that. Whereas x minus 3 has got a 0 at 3. And it will be positive to the right, negative to the left. So it means that this function f at x below 3, positive times a negative, will be negative. Above 3 is positive. And we want where it's going to be positive, greater than or equal to 0. That's in the question. So our answer in interval notation, inclusive, is from 3 upwards forever. So be aware of that. We'll see that again. Now the next thing I'm going to do is just take a few minutes to go through a graphical representation of these. And this is similar to what we saw before, so it's not really a big deal. But if you were to take a look at x squared minus x minus 6, find out where is it positive, all you do on your calculator is sketch y is equal to x squared minus x minus 6. And if you graph that, call it y1, say, you'll get this. And the question is, where is y1 greater than 0 or above the x-axis? Because that's where it is greater than 0. And here's your function. And you can see it's going to be greater there and there. So by inspection, where x is greater than 3 or x is less than negative 2. So anywhere the function is above the x-axis, then it's going to be, that's what we're looking for, where it's positive. So I'll leave it at that. The next lesson will be on rational inequalities, which really work under the same principle. They're just a little more things can happen with them. So thank you for your time.